Good afternoon, Year 13s. Thanks for coming along, guys. I've got 3 people waiting already, which is really nice. Be nice to see you guys pop up and say hi on the chat. That'd be really lovely. Today I'm going to be going through the Edexcel International A-Level January 2021 Paper 5. Say hi on the chat. That'd be really lovely. Yeah. Today I'm going to be... Okay, guys, so I'll close that down now. That's all working. Now, guys, I am very, very aware that paper 5 is the hardest paper you will ever sit. And what I will try and do today, I haven't seen the hidden materials, but what I will do is I will just point out regions of the specification that I know Edexcel are very, very, very driven on towards Unit 5. Having done enough of these papers now and been teaching this now for the last 5 years, it's very obvious that they have certain repetitive things that they do kind of every year or every other year. And so it just gives you a little bit of direction of focus for your studies and things just to make sure you've brushed up on. Now, this paper 5 is tricky. I had a skim through it earlier and I came across a question, which I'll flag up in when I go through this, which is incredibly challenging. And I'll, as I said, I'll talk you through it as best I can. Okay, guys, let's crack on. Let's share screen and flip to my clip cam. Let's crack on with this. Paper 5 is always a long one. I expect this webinar to be about 2 hours long by the time I've finished marking it and getting all the way through it. But let's see how we go. Got my water on standby. Try and put me a little bit more central. Got my water on standby. I know this paper's tricky. Hi, sir. I have Unit 3 today. Unit 2 was good. Ah, Sasha, I'm so glad. Did my videos help? So, Sasha, if you've just had your Unit 2 and your Unit 3s today, good luck with the Unit 3. Make sure you've had a look through my Unit 3 from January 2021. I hope that's really helpful to you. This is the Unit 5 one. This is the hardest chemistry paper that my students will ever sit. Unit 5 is always a challenge, it really is. Okay, let's crack on, folks. Let's crack on. Right, switch to, oh, I've got to make sure that my stupid screen's all connected. My power's just become disconnected. My screen's going crazy. It's flickering on and off. It's because I've, one of my connectors is like a cheap Lazada thing. Yes, they were very helpful, thank you. Oh, I'm really glad that they were. Right, so this is the paper 5, guys. This is the A2 paper 5, hardest paper there is in A-level chemistry. Paper 6 is a lot easier, very repetitive, very easy to predict. And I'll do that over the weekend as well, get that one boxed off. Okay, right, section A, multiple choice. Let's crack on, folks. Trying to sort out all my stuff so it doesn't make too much noise. Okay, when an alkene is added, let's switch over to red. I like to do these in red. When an alkene is added to a solution of potassium permanganate, the purple solution turns colorless in terms of oxidation numbers and oxidation change and electron transfer. Right, so this is a very common redox titration for A-level chemistry. And we're going from the purple potassium permanganate, this is our purple color, to our Mn2+, which is colorless. And obviously the manganese is in a +7 oxidation state, going down to +2, so it's gaining electrons. So it's either now A or B, and it is, of course, the oxidation number is decreasing. So nice, easy start. Next, the standard hydrogen electrode uses an electrode of platinum coated in a finely divided form of the metal called platinum black. What is the purpose of the coating? It's to act as a catalyst. That's straight off the bat. I'm not even reading my choices. I know that the platinum in those in a fuel cell is acting as a catalyst, so it's there to increase the rate. So increase the rate of the equilibrium between hydrogen gas and hydrogen ions. There's my answer. To provide an inert coating for the electrode, nope, that's not correct. To increase the electrical conductivity of the electrode, nope. To ensure that the condition remains standard, nope. So A, definitely the right answer there. Next, the electrochemical cell is set up to measure the E cell of the following reaction. Okay, so, and it says, which is the cell diagram for the reaction? Okay, so we're going to run raw. Line, 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 line. This is how I teach it. So we've got iron going to iron 2 plus. So iron going to iron 2 plus. And we have tin 2 plus, tin 2 plus going to tin. So that literally is the picture that I now draw from that equation. And we go reduced, oxidized, oxidized, reduced. And we know electrons are flowing in that direction. That there is pretty much the entirety of cell notation as I teach it. And yes, I know line, 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 line. It seems a bit ridiculous, but it's just, it works. We wouldn't need a platinum electrode on either of those because we've got tin metal and iron metal. So just look for my cell diagram that matches mine. So yes, that works, but then that's going in the wrong direction. So A's out the window. That's now going in the wrong direction, so that's out the window. That one's going in the correct one, and that one's going in the correct one. The answer is C. And we're done. I like it. Nice and easy. Nice and easy so far. The standard electrode potential of Fe2 plus on the electrode is this. Okay, so we can see that from that reaction that we've got the positive electrode is here, and the negative electrode is here. We know this because electrons flow towards the most positive in a battery. Yeah. So what that means is that the tin is more positive than the iron is. And they've told us that the iron electrode is that. So in order to give us a cell voltage of plus 3 volts, what that means is that the tin must be more positive by that number. So what I'm going to do is I'm just going to go on my calculator, minus 0.44 plus 0.3, and I get an answer of minus 1.4. Minus 0.14. The answer is B. This has been a nice, relatively nice, easy start to the paper in terms of like usually the first ones are pretty challenging just to slow you down, but so far all okay. A hydrogen oxygen fuel cell can operate in acidic or alkali conditions. What is the reaction at the anode? Oh, okay. First one of any challenge. Okay, guys, so I'm going to do a little bit of explanation for this to get to the answer. So the first thing is that certain facts about fuel cells, which are really useful. Yeah, fuel cells, which can be the hydrogen fuel cell, a methane fuel cell, and a methanol fuel cell. There's a boatload of these fuel cells. But the first fact that you learn about fuel cells is that the fuel is being oxidized. That's kind of the point of it. Because in a fuel cell, you pump in your fuel on one side, and you pump in oxygen on the other. And what's happening is it's a type of combustion reaction. Yeah. And this reaction is being activated via platinum catalysts on the membrane. But essentially, the main process here is that fuels are being oxidized. Now, so the first thing is I recognize that this is what's happening, what reaction is occurring at the anode in the hydrogen oxygen fuel cell. Okay, the next thing then, of course, is which one's the anode and which one's the cathode. Now, that's actually a bit more tricky because the way I remember this, which is a bit of a nightmare, is I remember electrolysis. Now, electrolysis is the opposite of a battery. It's the opposite of a cell. Yeah, because what you have is you have the anode and the cathode, and what's happening is the cathode, which is negative, because it attracts cations, and that goes through reduction. And on this side, we have the anode because it attracts anions, and these go through oxidation. Now, electrolysis is the exact opposite of a battery. It's actually what happens when you recharge your battery. Yeah, that's literally what's happening. They reverse the process. Now, what that means is because they're the opposite in a battery, because the reaction's occurring in the other direction, because electrolysis, you split or you're recharging a battery. But then the battery is the spontaneous reaction going together. So it's reversed. So what's now happening is at the anode, instead of oxidation, you now have reduction. This is because the reaction is being used to drive the opposite direction. Instead of using electricity to do something, and that's oxidation, instead of being able to use yeah, instead of using electricity to split something, electricity is being produced by something coming together. So they're exactly the opposite. So it says here the anode. So the anode at this point, I go, right, the anode is the opposite of electrolysis. It's going through reduction. Now, reduction is the gain of electrons. So in this case, got to be really careful with this. Anode, oxidation is loss. Reduction is gain. The anode. Okay, I might have just got that backwards. Fuels are always oxidized, and oxidation always occurs because I hate these battery questions. I feel like there's something I've made. There's something niggling in my mind here. I seem to remember another trick here, which I don't like, which is the fuel. I thought the fuel, I was expecting this to turn out to be the fuel going to the anode, and the oxygen goes to the cathode. I remember because the anode was shorter. The word anode is short, and I always remember fuel goes with that. And so at this point, I'm looking at this, looking for the fuel, and the only equation with the fuel in that's going in is D. But that then would suggest the fact that it's going through reduction. But the fuel's oxidation. Oh, sorry, oxidation is loss. The fuel always goes to the anode. I've made a mistake here, guys. Straight away, already on a paper 5, I've hit a roadblock. They are the opposites. But are they opposite names, or is oxidation still? Because that suggests that the oxidation is still happening at the anode, which is, I think, which is why it's called the anode. The cathode always sees reduction. And in a fuel cell, we've got hydrogen gas being oxidized to H+ and giving away 2 electrons. And on the other one, we've got oxygen gas going to form water. It's an alkali one, so it's actually going to form OH-. My laptop's now decided to have a break already. Really irritating. Okay, the answer's D, because it's the only one with the fuel that's being oxidized. But the first one of interest, of which I'm going to need to review at that book. So hang on a minute. No, that's not the right thing to do here. I know that I wouldn't be able to do this in an exam. Hi, Meter. I've already been stumped, Meter. Paper 5. It's hard. So fuel cell, anode, cathode. That's the thing to look up here. Images. So in a fuel cell, the fuel is being oxidized. There you go. And it's being done at the anode. Okay, I did think that fuel went with anode and oxidant. Yeah, okay. So the answer is definitely D, and I've got something reversed in my other thinking. Where's the camera? Oh no, is my camera cut off? Oh, start cam. There we go. I'll bring it back on. I'm having a couple of issues, Meter, with my camera. Yeah, it's my there we go. Start cam. It'll come on now. There you go. It's a problem with the connection on my thing. I need to clean it. Okay. Next, which of these has the greatest number of unpairs electrons? I'm just going to move past this one and say flag it as I might have made a mistake. I haven't now at that point, but it's fine. Which of these has the greatest number of unpaired electrons? So we've got, it's going to make us go through all the table. We've had 4 easy ones. It seems reasonable for them to be mean to me at this point. The A-level table. So I've got chromium, which is there. And let's just do the outermost, since that makes more sense to do. So we've got argon, argon, and then it becomes 4s1 3d5. Now, just to tell you that this is an oddity. Chromium is one of the oddities in the chemistry table, so is copper. Yeah, so this one now has 6 electrons, which are unpaired. Iron, number 56, argon, 4s2 3d6. Now that has 4 unpaired electrons. I'll explain this a bit more in a second. Manganese, argon, 4s2 3d5, and then vanadium, 4s2 3d3. Right, I'm now going to explain this. And now that I've written those out, I now need to turn them into boxes. Yeah, and this guys, some long answers take more time than others. So chromium, as I said, promotion to fill. You'd expect chromium to have that, but it doesn't. It actually has this. So that has 6 unpaired electrons in it. Iron, and yes, this is an absolute fiasco in terms of the amount of time it takes. 2 and then 1, 2, 3, 4, 5, 6. 4 unpaired electrons in its outer shell. Manganese, 4s2, no unpaired, and then that's got 5 electrons that are unpaired, and then because these are all unpaired in manganese, yeah, and then vanadium has only got a few, hasn't it? It's not as many. It's got a pair there, but then only got 3. So the answer is chromium, but took quite a while to get there. Mr. Duncan, man, you are doing something profound for all of the US. For all of us. Thank you. It's a pure sacrifice. Zakaria, it's great to see you. Thanks for coming along. Yeah, it's really nice to have you here again. Nickel is classified as a transition metal. This is because nickel is a d block element. Nope. It has partially filled d orbitals. Nope. Forms stable ions, and there's my answer. The definitions. That's just nice. So God, spending a bit of time doing this one and the fuel cell one, like, I then have a nice and easy one, which is just a pure based on the definition. So we know that the definition of a transition metal is an element who can form stable ions with an incomplete d subshell. Nice and easy. Let's move on. Platinum forms a complex with the formula PT. Ammonium chloride forms this one. What are the shapes of the complexes? Well, this one is square planar. Just got to know it, I'm afraid, folks. And this one's tetrahedral. So we've got D. Nice and easy. What is the bonding between the ligands and the central atoms of these complexes? They're all dative covalent. The whole point of a complex is that you have a transition metal ion and it forms a dative bond to a ligand. Yeah. So it's just nice to mention that, and they're both complexes that I recognize. Just to tell you, by the way, that platinum, of course, is used as is used in chemotherapy, cancer treatment, and it has no color, by the way. Well, actually, I don't think it might be yellow, but you're not expected to know that one. The copper chromium tetrachloride, I don't know the color of that one either. You don't learn those ones. That's interesting. Next. Cobalt chloride is used as the test for the presence of water. Yes, anhydrous cobalt chloride is blue and hydrated cobalt chloride is pink. There we go. Cobalt chloride paper starts off blue and turns pink, I believe. Yes, because cobalt in solution is pink, blue, 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 straw yellow, pink. Yeah. So start the anhydrous. That's a clever one. Technically GCSE that. That's the test, the alternative test for water. Usually you use anhydrous copper sulfate, which then goes from white anhydrous to blue hydrated, just to mention. Nice chemical test one there. Iodide ions are oxidized by peroxo disulfate ions in solution. Okay. The reaction is catalyzed by iron 2+. And this catalyzes for, okay. So guys, just to explain this one. So this is homogeneous catalysis. Yeah, homogeneous catalysis. And just to explain what's going on here. So the first thing is, this is a very common homo-cat question. Homo-catalyst question. And what's happening here is the iodide ion reacting with the peroxo disulfate ion, which is this guy, to form iodine and SO4 2 minus. Now, for those people who haven't watched my homogeneous catalyst lessons, I don't know whether or not I've done them on YouTube. I've mentioned it in my channel for sure, but whether or not you've seen it is another thing. Now, this is worthwhile mentioning. These questions do come up. By the way, I need to balance the charge. There you go. So just to explain what's happening here. So we have the catalyst is Fe2 plus and Fe3 plus. Now, this is what I call the cat box. So what can happen is the iron 2 plus can lose an electron to form iron 3 plus. Yeah, and then the iron 3 plus can gain an electron to form iron 2 plus. Now, they can do this because they're both pretty stable in solution. It would prefer to be iron 3, but it can easily move between the two of them. Yeah, so these are what are called my cat equations in my cat box. Now what I can do is I need to split this up. So the iodide ions are going to form iodine. Let's balance the half equation. Loses 2 electrons. I'm running my way, by the way, here, guys, when I'm balancing these equations, just throwing it out there. And then what's going to happen is the S2O8 2 minus ion goes to 2 SO4 2 minuses. Now I can balance that half equation as well. I'm just going to move the cat box down a bit. This is my cat box. So then I balance this one, which is all the atoms add up. It just doesn't add up for charge. That one gains 2 electrons. Now what I do is I multiply my cat box to give me the right number of electrons. So I'm just going to multiply everything by 2. Now this equation here, the first equation, gives me 2 electrons. And the equation that needs 2 electrons is this guy. So I now put those 2 equations together. So I'm now going to have 2 Fe2 pluses plus S2O8 2 minus goes to 2 SO4 2 minuses plus 2 Fe3 pluses. And that now eliminates those 2. Next, this equation here requires 2 electrons, and this one needs 2 electrons. They now go together. Yeah, so this cancels with this and put the 2 equations together. So I now have 2 Fe3 pluses reacting with 2 I minuses goes to 2 Fe2 pluses plus iodine. And those are my 2 equations for the catalysis of that reaction. And guys, this comes up about every other paper, and it's worthwhile doing a bit of learning on the understanding of how to first of all build a cat box, and secondly, how to split a reaction into their 2 and combine them. It's really important. Have a look at that. So in this case, this reaction is catalyzed by Fe2 plus. Why? Because Fe2 plus reacts with iodine, and no, that's not correct. It doesn't react with both. Fe2 plus has many electrons, and no, it doesn't. That's garbage. Fe2 plus has active sites. No, it's not heterogeneous. Fe2 plus is readily oxidized to Fe3 plus, which is then reduced to Fe2 plus. And there's my answer. I'm not being very consistent in my colors for my answers, am I? As long as I mark in green, I'm happy. Okay, the delocalized electrons in benzene results from the overlap of p orbitals to form a pi bond. Okay, so this is the idea that you get 2 pictures of benzene. Yeah, you've got this one. This is not benzene. This is 135. Hang on a minute. This is cyclohexa. Needs the A because it's a triene. 135 triene. Now we know if we compare this with benzene. By the way, paper 5 is always heavy benzene, so just bear that in mind, folks. Learn your benzene bits. So we've got these 2 pictures versus each other, and what we actually realize is that the energy, if you look at the energy profile of this, you have cyclohexane down here. Now, they always talk about the hydrogenation of benzene. They're going to take if you have the cyclohexa 135 triene, it's up here, and we're going to add 3 hydrogen molecules to this, and you'll get this graph, and this is the enthalpy change. Yeah, but what we realize is benzene has delocalized stability, which means benzene's actually much more stable, which means the enthalpy change is smaller than expected. This is because of its delocalized stability. Yeah, you'd say the electrons in the double bonds become delocalized, which provides it with delocalized stability, meaning no matter what happens to this molecule, the energy to get to the product is going to be less than expected. Let's move on. The reaction of ethene with bromine under normal laboratory conditions and the reaction with benzene and bromine requires heat and a catalyst. The best explanation for the difference in reactivity is the delocalized electrons in benzene. Yes. They repel electrophiles. No, they don't. They don't repel they repel nucleophiles. Benzene repels nucleophiles because nucleophiles, I'm just checking if my camera's still working. Benzene, of course, is electron dense, so any nucleophiles that are negative are going to be repelled, but it's certainly not going to repel electrophiles. Results in a kinetic barrier to the intermediates. Yes, that is correct. So I'm going to just check the others first before I tick it. Results in benzene having an endothermic enthalpy of formation. Most enthalpies of formation tend to be endothermic. Enthalpy of formations. Most of them tend to be exothermic. It depends what you're making. In organics, they're usually endothermic. In ionics, they're always exothermic, or most of the time. Question mark. Make benzene thermodynamically stable with respect to the formation of bromobenzene. No. Make benzene thermodynamically stable with respect to the formation. Make benzene with respect to the formation. What? That sentence doesn't even make any sense. No. So, okay, let's just chat about the reactions of benzene. So we know that an alkene, if you have an alkene, right, and you react it with bromine water, yeah, what happens is the double bond reaches out and we go through electrophilic addition. Yeah, the double bond reaches out, yeah, and you form an odd cation intermediate, the bromine's here. Yeah, and then this is actually not with bromine water, by the way, but anyway, it doesn't. So they add on. This is EA. Yeah, this is electrophilic addition. Now, benzene doesn't do this. Thank you so much for solving the paper. Lyrics World, you are very welcome. I'm not doing a particularly good job of it at the minute. Well, at least I'm trying my best to explain the bits. This is going to be a really long webinar. I think I'm going to hit over 2 hours here because I'll tell you why, Lyrics World. And Mita and Zakaria and Sasha, the reason why I'm taking a bit more time on this is because paper 5 is by far the hardest one. And I've got a feeling, I haven't seen the hidden materials, but I've got a feeling that there's going to be similarity between this paper and the paper coming up that I haven't seen yet. So it's worthwhile me just having these discussions. Yeah, so we know that alkenes usually go through electrophilic addition reactions. Now, benzene doesn't. Benzene won't react with bromine. Now, the reason being is that even though bromine becomes polar upon collision, yeah, so bromine is non-polar to begin with, but then it collides, the electrons shift, and it becomes polar. But here's the thing. For the electrons to reach out of benzene and take that bromine won't happen. And it won't happen because the electrons are being shared between all the carbon atoms in here. So instead of dragging the electrons from only 2, yeah, instead of dragging the electrons out from 2 carbons, you're dragging them out from 6. And they don't want to do that because you're going to end up with an unstable intermediate. Yeah, you're going to end up with this picture, yeah, with the ring broken around that and the bromines attached and the H there, by the way, that breaks there. And this won't happen. And that's the kinetic barrier. Yeah, you've got to rip those electrons out from the benzene ring. They don't want to do that. And that is a kinetic barrier. I don't like the word kinetic. It's more like a thermodynamic barrier, in my opinion. But what we can do is we can add a catalyst, because it's not a good enough. And by the way, the catalyst is the bit that explains the kinetic bit, because the catalyst for this is AlBr3 now, or AlCl3. You can actually use AlCl3. But what that will do is it will react with bromine. It will rip off a bromine to form AlBr4 minus and Br plus. Now that is now the electrophile for benzene. Yeah, this is the electrophile. And it now can react with that as Br plus. Yeah, it can now have enough energy to be able to pull those electrons out the ring. So it is a kinetic barrier here, folks. Just to also mention, it's a kinetic barrier. Just to also mention some other people of interest. So one of the things that I really, really want you guys to spend a bit of time looking over, wouldn't it not be a thermodynamic barrier because the total entropy still increases? Julian, hi Julian. Everybody, Julian is a student of mine here in Malaysia. He's a very good chemist. I don't think it's going to be a problem from an entropy perspective. I thought this just affects the activation energy. Yes, but Julian, consider what you've just said. Activation energy is to do with kinetics and rates. Yeah, you don't talk about catalysts thermodynamically. Yeah, the only time you ever come across it is activation energy. In the Arrhenius equation. But in this case, this is much more important to look at it from a kinetics perspective. And you're right, from an activation energy perspective, which is a kinetic issue. You wouldn't bother talking about the entropy changes, because the entropy changes are all small really in this particular scenario. Yeah, there's not enough people and there aren't any gases. These are all dissolved in solutions and liquids. The entropy change will be very small. Just to also talk about some of the other people. So other people include things like methyl benzene. Now, methyl benzene is activated. It more readily reacts with compounds, because the CH3 group is an activating group because it has the positive inductive effect. Other ones include phenol. Phenol is an important one, guys. Please do some research on the reactions of methyl benzene, otherwise known as toluene, and phenol. Yeah, I'm trying to think of other ones that they commonly ask. Nitro groups as well. Look up the nitros, but also consider, the reactions with bromine. I can't remember like all of the reactions with these, but phenol is something I would look into. Things like it reacts. So phenol. So benzene doesn't react with bromine water. No, alkenes do react with bromine water, and phenol reacts with bromine water as well. But in the presence of bromine, it goes through all kinds of funky additions to form white precipitates of things like, you'll get a monosub, and they're all directed, by the way. So you end up with a bromine here, and then a bromine here, and then a bromine here. It's worthwhile looking into that. I believe that's a white precipitate. But it's certainly worth looking into the reactions of phenol and methyl benzene and nitrobenzene. Do some benzene research. Yeah, we know it's always on paper 5. It's always there. Same thing with transition metal colors. We know that they're going to be there as well. Yeah, next, let's move on. What is the name of this compound? Okay, that was nice and easy. Well, it's an amide. Let's count the carbons. So 1, 2, 3, 4, and a branch. So we've got, this is butan amide, butanamide. Yeah, and the amide group is here, and that's carbon number 1, so this is 2-methyl. 2-methyl butanamide. Moving on. Separate 0.1 moles per dm cubed aqueous solutions of ammonia. But in order, we've done this before, Donna. I think I've seen an MCQ where the benzene reacts with Br2. You'd need a catalyst, Donna. Yeah, you'd need a catalyst. It won't do it without it. You'd have to find the MCQ, Donna, because there's going to be clauses all over the place. You can't say stuff like that, Donna, without being able to have the question. Come on, sort yourself, Donna. It's nice to have you here, by the way. Increasing pH, we've seen this a lot. Ammonia is pH 11. You need to know that. Phenylamine, that has a pH of about 8. And then butylamine has a pH of about 12. Now, if you're wondering how I know that, okay, so here's the thing. The first thing is ammonia. Ammonia, you've just got to know, is a weak base. And it's really useful to know it has a pH of 11. It's really handy. Now, the reason why this is useful is because when you then go to primary amines, where you add on a carbon, like methylamine, yeah, this actually becomes a better base. The reason being is that the carbon group has what's called the positive inductive effect. It pushes its electrons towards the nitrogen, and the lone pair on the nitrogen then moves away from the nitrogen and becomes more available. And this now has a pH of about 12. It goes up by 1 from the ammonia. Yeah, I've done too many papers, I can't keep track. Oh, Donna, well done for doing the papers. I've lost my mouse. Hang on a sec. Your message is hidden. Give me a second. I've lost my mouse. Oh. Where's it gone? There it is. Found it. Sorry. Donna, I just want to unhide your question. Yeah, I know the feeling, Donna. I feel like I've done too many as well. I've been doing the GCSE and the AS ones along with the A2 ones. It's hard. Next thing, guys, is that the CH3, if you go to a secondary amine, the pH goes to 13. This is because you've got the positive inductive effect pushing those electrons even further out. They are more available. Positive inductive effect, lone pair more available. Yeah, better base. Then you go to the tertiary amine and all of a sudden the pH drops through the floor. Yeah, this one's a really clever trick. This is like pH 7.5. So you'd expect it to be a better base, but the thing is it's now not soluble since it no longer has hydrogen bonding. And then you get something like phenylamine. The last one, we always talk about phenylamine. Phenylamine, again, has a pH of around about 8, 7, 8. And the reason being is the lone pair on the nitrogen becomes incorporated into the ring. Yeah, you need to know those words. Yeah, lone pair on nitrogen is incorporated into benzene's delocalized ring. They are no longer so less available. Poorer base. We're done. It's nice to talk about those. So it's nice to explain these little tricks. So the increasing pH, the lowest is going to be phenylamine. Yeah, so it's either going to be, so there's only one answer. Done. Increasing pH. Thank you very much. Moving on. Next, monomer. Right, so this is an addition polymer. It's a polyalkene. Put the double bond back. Nice and easy. Yeah, so I can get rid of him and get rid of him. And there's my picture. So it can only be, it's either A or C, since those bonds no longer exist. Because this was the alkene, remember? Yeah, this is the alkene. And then these lines here appeared because of the result of the double bond breaking open. I hope that makes sense to everybody. These don't exist. Yeah, so it is no longer C or D. Now I need to get the right one between, there's some kind of methyl branch going on here. So if I was going to draw that out, that's what I would draw. It's an enamide. Isn't that interesting? If you want the name of it, 1, 2, 3. Proptuenamide. Isn't that funky? So where's that? I don't know why they're trying to put a branch on this. There's no branch anywhere. So the answer is A. Moving on. Next. The repeat unit of the polymer shown. So cut it. It's a polyamide for a start. There we go. So we've got an amino acid here, but then that is not an amino acid. So this is a polyamide, but not a polypeptide. Because in fact, it can't be a polypeptide because these aren't amino acids at all. This is a dioic and a diamine. So it's definitely not a polypeptide. So this is a polyamide, but not a polypeptide. D. Yeah, polypeptide and polyamide, no. Neither, well, that's stupid because it's a poly and it's an amide linkage. Yeah, there's the amide linkage, folks. And a polypeptide, but nope. The answer's D, definitely. Right, C13 NMR, how many peaks will there be? Straight away find your symmetry and count on or over the line. So 1, 2, 3, 4, 5. Moving on. That was easy. That's the way you always do NMR, guys. Look for symmetry. Next. When a sample of a hydrocarbon is burnt completely in oxygen, 2.64 grams of carbon dioxide and water are formed. What's the molecular formula of the hydrocarbon? Okay, so a bit of a pain in the ass, but we've got CO2, moles, grams over rams. Carbon dioxide weighs 44.0. I've got water, which is 0.81 grams over 18.0. I'm just going to work out the moles of each of them. 2.64 divided by 44 gives me 0.06 moles of CO2. Now, this is also the moles of carbon because each carbon dioxide has one carbon in it. So if I had one CO2, I had one carbon. Next, I now have 0.81 divided by 18. Gives me 0.0505 or 506. Now, this is moles of water, and we want atoms of hydrogen, and there's 2 per water, so times that by 2. And I now get 0.101. Right, divide them all by the smallest. 0.06, 0.06. That gives me 1. So we've got 0.101 divided by 0.06 equals 1.68. 1.68. Now that's 2/3. Multiply everything by 3. So C3 doesn't add up. I'll stuff that up, haven't I? It's completely burnt in oxygen. What could be the molecular formula? It's molecular, not empirical. So the empirical formula is C3H, I'm going to times that by 5. C3H5 is the empirical. What could be the real one? That really doesn't work out at all. What have I done wrong? When a hydrocarbon sample is completely burnt in this much carbon dioxide, 2.64 over 44. Have I done a maths wrong? No, I haven't. That's the moles of carbon. That's therefore the moles of carbon. Is the right answer, 0.06. And then 0.81 divided by 18 gives me, I've literally written down the wrong number, which gives me, how do I want a calculator error? 0.045, made an error. Yep, times that by 2. There we go. Guys, it's so easy. That was literally a calculator error. It's a calculator error. So divide them now all by the smallest. 0.06 divided by 0.06 gives me 1.5. Right, times it by 2. Right, so C2H3. So what could it be? It could be C. Done. Because I could double that to form the molecular. Does that make sense? I've worked out the empirical. Yeah, the empirical, and it's given you the choice there of the empirical there, but it can't be a molecular because you can't get C2H3, it doesn't exist. But what I could do is double it, and I get C4H6. I can't get any other extra from that, So it seems reasonable for me to go to C. Let's go to the next one. Okay, benzene going to methyl benzene, going to benzene carboxylic acid. Ugh, powerful oxidizing agent to do that. Not sure on how they do that transformation in step 2. Need to look that up. So we've got 8.24 grams of benzene carboxylic acid was formed. 8.24 grams. What was the mass of benzene used? Okay, fine. Grams over rams. It's even given me the MR. Not even to 1 decimal place, the losers. 8.24 divided by 122. Calculator's sticking. Gives me 0.0675. Right, well, it's a 1-to-1 to benzene. Ratio is 1-to-1. So I'm going to make the same amount, 0.0675. Right, multiply that by the MR. 5.26, 5.27, B. Moving on. Seems reasonable enough. That brings me to the end of the multiple choice section, which I've spent a lot of time, 45 minutes. I've spent a lot of time there, guys, focusing on, please look up these transformations as well, folks. By the way, that one there is an easy one. That's electrophilic substitution using AlCl3 as a catalyst and a chloromethane. Yeah, extending the carbon chain on benzene. Anyway, let's continue. It's going to get harder. Right, so all the colors in the world. Now, this is my favorite bit. It's the easiest bit in chemistry. Just learn your colors, folks. Like, if you don't learn your colors, then, well, don't expect to get any of these marks. Yeah, so starting off, this is copper compounds. So the pink solid, that's copper metal. That's easy enough. Copper metal. I'm actually going to write down copper metal. Do I need to include the identified by name, including the oxidation state of the formula or species subsequently containing copper? Oxidation state 0. Oxy state, so stupid. Let's write down that every time. 0. Right, so we've gone from copper 2 plus, copper 2 sulfate, a blue solution, and we've now added Ki. Now, Ki is a reducing agent, and the iodide ions have actually reduced the copper from copper 2 to copper 1 iodide, which is colorless, by the way. Yeah, they then add sulfuric acid. That acts as another reducing agent, taking it all the way down to pink copper metal and a blue solution. So the blue solution, by the way, is going to be back to copper sulfate. It goes through disproportionation. Copper 1 tends to go through disproportionation. So the Q is going to be identity by name or form. I'm actually just going to put Cu solid because I identify by name or formula. Cu solid. This one's going to be, so hang on a minute. The color for the blue solution. So it's not copper sulfate. It's the copper 2 hexa aqua ion. This is unit 5, folks. Yeah, oxy state +2. Yeah, remember. You've got to remember that colors come from their complexes, not from something like copper sulfate. Yeah, it's the copper hexa aqua that's blue. Right, next, let's go to R. So in R, they've added ammonia aqueous, and it's formed a pale blue solid. So it's acting as a base here. Yeah, so what that now does is it takes the copper hexa aqua copper 2 complex, and what it does is the ammonia acts as a base. 2 of them rip off 2 hydrogens off water molecules. And what I form is CuH2O4OH2. And that is my pale blue precipitate because it's electrically neutral. I also form ammonium chloride. 2 of them as ammonium ions there, guys, as the byproduct. But I'm forming the pale blue precipitate of the tetra aqua dihydroxy complex. So this is Cu brackets H2O4 close brackets OH2. I like it. Oxidation state of the copper is still +2. Yeah. Next, now we go to S. Now, when you heat that solid, you form a black solid. Well, there's only one black solid in copper that I know of, and that's copper oxide. And that has an oxy state of +2 as well. Oxy state. Just got to know your people. Just got to know your species. So I'm assuming that they're not going to ask copper in the next one. I don't know what they're going to ask on the next one, folks. But I'll do a little bit of teaching on this regard in a second as well. Next one, the pale blue, and they've now added more ammonia, and they formed a dark blue solution. By the way, aqueous ammonia wouldn't work there at Edexcel, idiots. So T is going to be forming the copper, the tetraamine diaqua complex. I'm going to draw that one for you. And that still has an oxy state of +2. Notice that copper is always +2 or +1, and if it's +2, it's got a color. Yeah? I ought to put them in brackets. +2. Electrically neutral. Copper oxide, no brackets needed. Just to explain what's happening here, this is because now this one we're seeing a change in color due to a change in ligand. Yeah? We know there are 3 reasons why you can change. Technically, actually, there's 4 reasons how you can change the color of a transition metal solution. So if I have a beaker and it contains a TM, yeah, let's choose someone. Let's choose copper. Let's not go to copper. Let's go to someone more interesting. Let's go to chromium. So if I have chromium 2+, by the way, which is the hexaaqua, everything starts off hexaaqua, yeah? And it's 2+, this is blue. Now, if I change that to chromium 3 hexaaqua, yeah, if I change that there, then I become green, yeah? So one of the reasons for the change in color, I always love this, color. The word color, the first 3 letters. The first one number is coordination number. Coordination number. And in this case, that's not this, because the coordination of both is 6. The oxidation state, that's this one. Because I've gone from a +2 chromium to a +3 chromium, change in color. The next one is change the ligand. Yeah, if you change the ligand, then you change the color. So this guy is the Cu, yeah, and we've now changed some of the water ligands for ammonia ligands. What that means is we see a change in color. Yeah, that's a 2+, and it's a deep blue. The other way to change the color is to change the transition metal. Now, just to say why it does change color, why do these things change? You can also change the TM. But if you change the coordination number, yeah, copper tetrachloride, yeah, coordination number 4, yeah, or we have the copper hexaaqua, coordination number, they're waters, OH2, yeah, all waters, water. This has a coordination number of 6, but I've also changed the ligand. In this case, there's 2 reasons, yeah. The oxidation state's the same, both 2+. That's 2+, these are minus. The overall of this is 2-. And then this one, of course, is the copper is 2+, so that's 2+. But just to tell you, when you change the coordination number, when you change the oxidation state, when you change the ligand, you change the D block splitting. Yeah, we know that the D block of elements, the D block with the electrons in it, the 5, yeah, the 5, when you form a complex, the D block splits. Now, when the D block splits, the electrons can become excited by absorbing visible light. And it's this gap that decides the color of light absorbed. If you change any one of these, you will change the D block splitting. Therefore, you will change the frequency of light being absorbed, and you'll see a different complementary color. Yeah, so just bear that in mind, folks. So V, who's V? So I've gone from copper 1 iodide, shaken it with ammonia, and I've formed a colorless solution. I'm assuming with ammonia, when it's aqueous, what I'm going to have, oh, my laptop's done something strange. Hang on a sec. Sorry, my laptop's just jumped. And then we shake it vigorously and it turns dark blue. Okay. So what that means is I have Cu brackets. I've made a mistake there. It's 4. T is 4. Good catch there, Mr. Duncan. There we go. So this one is going to form the same thing, but it's colorless. Now, the reason why it's colorless is because it has a +1 oxy state. Copper in the +1 state is colorless. Hi, sir. I'm new to this channel, and I'm excited to learn from you as much as I can. By the way, call me KB. It's nice to meet you, KB. Thanks for coming along, dude. It's nice to have you join my channel. So just to explain to KB again. So know your colors, know your transition metals. There's a lot under Edexcel. There's an awful lot of them. Copper comes up fairly heavily, but just you've got to know your colors. And copper is a particular oddity because the copper 1 ion can be formed. It's rare. But like in this diagram, they have formed very specifically here, copper 1 iodide, which means it's colorless. Then they've shaken it with ammonia in aqueous, and it's going to form the complex. Now that complex will be colorless because that is still, this one is still copper 1+. Then they've shaken it vigorously and it's turned blue. It's been oxidized. It's been oxidized by the air in the water. Yeah. And W is that literally just going back? No, it's going back to T. Oh yeah. So what's this one? A blue solution. They've taken the black solid. They've just formed copper nitrate in solution, which is the hexaaqua again. God, can I just point out there's an awful lot of chemistry going on there. Yeah, which is now the blue solution again. Oxy state 2. Yeah. There's an awful lot of chemistry going on there. I hope what I've talked through, guys, makes a bit more sense. And that, you know, I'm only giving you snippets of my lesson here, but I'm just making you aware of them. From T to V, the same type of chemical species, name this type of chemical species. They're complexes. T, most of these are. T and V, they're all complex. Well, okay, hang on a sec. Let's highlight them. Complex. Don't want to do that. Complex, not complex, 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 complex. Loads of complexes. 5. Why would they pick out T and V? Stupid. They're trying to trick you there, folks. The only thing that is complexes. Okay, explain why T is colored while V is colorless. A detailed explanation of the fact that T is colored is not required. Explain why T is colored while V is colorless. T and V. Okay, the oxidation. That makes sense. So I need to get the, so V, because it's colorless. Yeah. V contains copper +1. This has a full D subshell. A full D subshell. I'm going to even give you a configuration. 1s2, 2s2, 2p6 back to the beginning. 3s2 skip over. 3p6 back to the beginning. 4s2, 3d. Now for copper metal, I'm just going to talk you through the copper metal. Copper metal people think it's this, but it's not. What it actually is 1 in 10. You get promotion. That there is copper metal. Yeah. Now we go to copper 1+. The copper 1+, yeah, will remove the 4s1. They will be removed. They disappear. What that means is it's got a full D, which means it cannot absorb, even if the D block splits, the gap between them doesn't matter because the electrons can't move around. There's no gap for them to absorb visible light. They cannot be excited. Yeah? So copper 1 has a full D subshell, so electrons, so electrons cannot become excited, so it cannot absorb visible light. Absorb visible light. Now he's shaken the tube. Yeah, he's shaken the container. Yeah, vigorous shaking. Now when he vigorously shakes it, oxygen is going to react with the copper 1+. So we're going to say, yeah, on shaking, you don't actually need to shake it, by the way. If you just leave it to stand, it'll do this. Yeah, on shaking, the oxygen dissolved in the water, or in the air. By the way, it doesn't matter. If you don't cork it, it'll always change color because the oxygen in the air will dissolve into the water. And that oxygen will react with the copper 1. Yeah, so on shaking, the oxygen dissolves in the water and reacts with copper 1+ and copper 1+ to form copper 2+, to form Cu2+. Now, the reason why it can do that, folks, is because the amount of energy it takes to remove that second electron is small. It's really, really tiny. So it's going to readily do it. And then once it removes that extra electron, it becomes more stable. So the energy to remove it is very small. Therefore, it's going to lose it and become a more stable ion. Does that make sense? Yeah. Be interesting to see what the mark scheme says for this. On shaking, the oxygen dissolves in the water and reacts with Cu1+ to form Cu2+. Full stop. Cu2+ has a incomplete D subshell, so can absorb visible light. Absorb visible light. And we're done. I'll do. Suggest an explanation for the change in V to T on shaking. I've given it already. Oxygen. By the way, can I just point out something? I've noticed a couple of things from my students doing tests recently that they would think, oh, I've already done this, so I'm just going to do this. That doesn't wash. You're not allowed to do that, guys. It will not be marked. Just telling you. Oxygen reacts with Cu1+ to produce Cu2+, which has a incomplete D subshell. So electrons, you're not allowed to do it in your exam, but I can now be excited, showing color. I don't think I need to actually do any of that bit again, but it doesn't matter, we're going to add it anyway. Next, the reaction between copper 1 iodide and sulfuric acid is a disproportionation reaction. Write the ionic equation for this disproportionation reaction. State symbols are not required. So we're going from copper 1+. Ooh, now that's interesting because they've given us no information about what the sulfuric acid itself is becoming. That's awkward. They from an ionic perspective, they just want us to go from that to Cu to Cu2+. That's all they want. Balance the equation. We're done. That's the ionic equation. That's it. I'm wondering, That's all I got. Show the reaction in CI is thermodynamically feasible using the standard electrode potentials and the relevant half equations from the data book. Okay, you mean person. Right, let's have a look. Where are you, data book? I downloaded the data book. Just move that there. Let's get rid of that thing. International data book. I need to try and split my page so you guys can see what I'm doing. The data book's not the easiest thing to work with. So let's now scroll down. I'm looking for E cell values. Indicators, there they are. So we need to prove that this is thermodynamically feasible. So what we need to find is copper 1 going to copper. Well, there's copper 1 going to copper. So there is Cu2 plus E minus goes to in equilibrium Cu plus. And then we have, so that's going, that's Cu plus going to Cu2 plus. And then I have, there you go, Cu plus going to Cu plus gaining an electron to go to Cu. Now, what that now means is we can now pull out their values. Got to be a little bit careful here. Because we've got Cu plus going to Cu2 plus. That's the first one. That's this one here, is this one. Yeah, and then this one is here. Let's find their values. So Cu2 plus going to Cu plus 0.15, and then Cu plus going to Cu metal, which is down here, which is plus 0.52. Okay, flip the more negative. Yeah, flip the more negative. Now that we've taken those out, yeah. So what we realize is that Cu plus, because look, if you flip the more negative one around, let's flip this one here is the more negative because that's the more positive. So flip this over. The rule is flip the more negative. Yeah, so this becomes Cu plus an electron. No, sorry. Flip it over. Cu plus going to Cu2 plus an electron. And that makes total sense because look, the electrons now cancel out, and when we put the equations together, we get the same thing. So the overall equation is 2Cu, which is the same as the one I've already written above, which is great. And so I'd write down these two equations like that in my exam. Yeah, this makes total sense now. And now I would say EARL. E cell equals right minus left. Yeah, and then if you realize that on the number line, electrons in cells always move. So this is the right-hand side and this is the left-hand side. So the right is the more positive one. So this is on the right and this is on the left, and it's right minus left. So EARL equals plus 0.52 minus brackets plus 0.15. And what we get is a positive cell value. Yeah. So we now go plus 0.52 minus brackets plus 0.15. And I get a positive value of plus 0.37 volts. This is very feasible. Yeah. Show the reaction is thermodynamic using the electropotentials and the half equations. That's fine from the data book. So positive, I'm making a mess of that. Positive E cell means feasible. I've gone mad. Means feasible. I hope that makes sense, guys. Hope that we found that useful. Next, good old calculation. A rare mineral, mitschurlikite, has the chemical formula here. Okay, yuck. That's grim. Water crystallization question? Really? Unit 5? They're going to make it hard. It's GCSE trick, this, guys. They're just going to make it really horrible. So it says so first thing is I'm going to copy down that formula just so I don't have to keep scrolling up all the time. In an exam, you don't have to because it's on paper, but that's fine. And I've got 4.26 grams of that, and that was dissolved into 250 centimeters cubed. Yeah, I then, each made up to excess potassium iodide solution was added to a 25 centimeter. So they've taken a 25 centimeter portion. Yeah, so there's going to be a times 10 somewhere. Yeah, and excess potassium iodide was added to this portion. Potassium iodide. Yeah, an iodine formed, was titrated against sodium thiosulfate of concentration. So we've now done sodium thiosulfate, which is Na2S2O3. Right, sodium thiosulfate, and its concentration is 0.05 molar, and the volume needed was 26.65. Nice and easy. Calculate the value of N. Okay, so step number 1, moles of thiosulfate. So moles of thio, is going to be C number of moles equals C times V over 1,000, because I'm in centimeters cubed. Moles equals concentration of 0.05 times by a volume of 26.65 all over 1,000. Nice and easy. Great, easy start. 0.05 times 26.65 divided by 1,000. And I get a moles of thio of 1.3325 times 10 to the minus 3. Okay, so I've now got moles of thio. Now I find the equation, and what you realize is that 2 thios react with 1 iodine. Now the iodine is then linked to this equation here, which will help me get back to the original copper. Yeah, so I need to get to the iodine. I could alternatively go to the iodide, definitely could, but I'll stick with the iodine. So that, because it reacts with him, so you use it all up. So it's a 2-to-1 ratio. So the next thing is, ratio, just right, I'm trying to save my space here, is 2-to-1 from S2O3 to minus to iodine. So I'm going to divide it by 2. Take that number, divide it by 2. Okay, so the moles of iodine. What you realize is I could have gone for the iodide. It wouldn't have made any difference. Yeah, moles of iodide is 6.66 times 10 to the minus 4 moles. Okay, now that I've got that moles, I can now, so to move within in an equation, you have to use the ratio, but to move between equations, you do absolutely nothing. So I've got 6.6625 times 10 to the minus 4 of iodine. Now the ratio back to copper 2 plus is a 1-to-2. So the new ratio is again, is a 1-to-2 to the copper and the iodine. So I'm going to multiply it by 2 again. It's irritating, isn't it? Moles of copper. Moles of copper 2 plus is multiplied by 2 again. 1.33 times 10 to the minus 3 moles. Oh, got to be careful. 10 to the minus 4. Oh. Just want to check that. Experiment divided by 2. Yeah, okay, times by 3. Sorry, 10 to the minus 3 moles, back again. Right, now that I've got that, that is now the moles of copper 2 plus. And what you'll notice is that in this compound, there's only 1 copper. So if I work out the moles of copper, I work out, hi Wenke, great to see you, dude. If I work out the moles of copper, I've got the moles of the whole thing. So I just need to remember that there's a times 25, there's a times 10 here, because this was in the 25 centimeter sample. So I need to get back to the 250. So I'm now at this point going to multiply it by 10. That becomes 1.33 times 10 to the minus 2 moles of copper in the 250. And all the solid was dissolved in the 250. So that is, that is the moles in the 4.26 grams of the whole thing. Now, at this point, we now have the moles of the compound. I now have 1.33 times 10 to the minus 2 moles of K2CuCl4.NH2O. Right, well, we can work out its MR because I also have its mass in 4.26 grams. Number of moles is grams over rams, and I want the rams. Your boy Danny, good to see you, dude. So I'm going to bring that up, bring that down, so it becomes grams over moles will give me rams. So I now have my grams of 4.26 over 1.33. Oh, darn it, I've lost it. There was an extra number there. 3 times 10 to the minus 2. What does it give me? 4.26 divided by 1.33 exponential minus 2. And I get a massive MR of 320.3. Okay, so there's my MR. Now I can work out, the amount of water, because I'm just going to substitute everyone else from it. So the first thing I'm going to do is I'm going to work out the weight of all of this bit. How much does this weigh? So potassium, 39.1, I believe. Potassium, 39.1. 39.1 times 2, plus copper, 63.5, plus chlorine at 35.5 times 4. So 39.1 plus 39.1 plus 63.5 plus brackets 35.5 times 4, close brackets, 283.7. So I'm now going to minus 283.7 from it. So 320.3 minus answer, and I get 36.6. Divide it by 18. And I get a value of 2.03, otherwise known as n equals 2. And I'm done. That was a long question, 6 minutes. I mean, I'm not rushing this. I'm taking my time. I'm talking it through with you guys. Guys, if you want me to explain any particular step, please just let me know on the chat. Happy to help. Yeah, I hope that made sense. I tried to make that as clear as possible, following it through. Can I just point out, by the way, lots of students would freak out at that question. They'd look at it and go, oh my God. Don't. Do the same thing I did. Draw out a simple sequence. And then just start from where you know. Start at the titration, find your moles, use the ratios, hop between equations, do nothing when you're going between equations, just within. Just transfer the number up. Don't forget your dilutions and your sample taking, but otherwise I'm happy. Next. Ketones are useful starting compounds in organic synthesis. This question is about butanone. The mass spectrum of butanone has significant peaks of 43 and 57. Give the people. Right. So whenever you talk about mass spec in organics at A2, you talk about fragmentation around the C double bond O. The C double bond O is very electronegative and draws the electron density out of it, and it weakens these bonds on either side. So whenever you have fragmentation patterns, we talk about major splitting around those bonds. So the question is, what's going to be number 43? Well, let's just cut it here. I know that that's 29, so that's not particularly useful. How much does this side weigh? So I've got 12 plus 12 plus 16 plus 3, 43. So there's my first peak. So I've got CH3, CO, and don't forget, give the structures of the species responsible. I'm going to actually give the structure. Why not? Happy to do it properly. There we go. So I have split it at this bond here. And don't forget your charge. People forget that charge. Watch out. Okay, so where do I now get 53 from? 53 needs to be larger. So I'm going to split it here and count that side. That looks like it could be 53 to me. 12 plus 12 plus 12 plus 16 plus 5 gives me 57. That's exactly what I'm looking for. So I'm now going to draw that one out. I'm going to do that in red again. So there's my C double bond. I'm going to straighten the chain out. Don't see, there's no problem with me doing that, but do not forget your charge. Okay, nice and easy. Next, give the structure of one other species you expect to be produced in this peak. Okay, so the other peak could either be 29 or 15. Either one, don't really care. Yeah, they will also be there and produce a different M over Z. So I will give the ethyl branch. Why not? Yeah, MZ. Yeah, and it's going to be that guy, and it'll have a peak of 29. Moving on. I didn't have any other 29s, did I? No. Okay. Because it's just a check, by the way. 12 plus 12. 12 plus 5. 29. The other one, if you're interested, is the methyl ion. We'll also get this one as well at an MR of 15. Very common. Next. Devise a reaction scheme to prepare propan-1-ol from butanone using no more than 4 steps. Identify the reagents and essential conditions for each step and give the name or structure of the intermediate. Guys, that question there is horrible. Now, in synthesis, can I just point out, in my opinion, that question is really evil. That's pure evil of Edexcel. Because the problem is, you're not really going to get carryover marks on these. It's going to be a mess. Because what we're doing is, from butanone, we're starting with butanone, and we're shortening the chain. We're starting with this guy here, and we're shortening the chain. Now, you don't really learn how to do that in a synthesis. You don't really learn how to shorten them. There was a previous question before where we saw that you can shorten, that you can add to chains. Things like benzene, you can add to it with acylation, but an alkylation. But you don't really learn how to shorten the chain. Now, the way that we do this, we need to get to propan-1-ol. That's what I need to get to. So, and this is how I would lay it out in my exam, by the way. Yeah. So what I'm going to do is, first of all, and this is really mean, guys, the first thing I'm going to do is I'm going to cut the chain using iodoform. So I'm going to use iodoform to cut chain. So in order to, it says reagents and conditions. So the reagents for this, which I'll do in a different color, I guess, I'll put reagents is sodium hydroxide and iodine. And we're going to heat it. Yeah. So we're going to heat it. Now, if you don't heat it, it takes ages. Yeah, we're going to heat. We'd probably heat under reflux. It's probably what we do. But we just need to warm this in reality. We need to warm it up. So now when you warm it up, what's going to happen is you're actually going to form an organic product of propanoic acid. Now, I will explain what's happening here, folks. You do not need a mechanism for this, but I will explain what's happening. So the iodoform test, here's what's going on. I have got this structure, and the structure I'm actually looking for is this bit on the end. This is what the iodoform tests for. Now, what it does is, the iodoform, what it does is it will cover all of those things. It'll actually snap that off, and it forms iodoform. And this is what iodoform actually is. It's triiodomethane. And it's an orange, it's a yellow solid is what it is. It's a yellow precipitate. This is iodoform, triiodomethane. It's a solid and it's yellow. Now, what you're left with, what people think they're left with, is this guy. They're like, well, hang on a sec. What goes on the end of here? Now, the answer is it'll actually pick up a hydrogen at the beginning and form an aldehyde, but water is present. Yeah, water is present and iodine. Now, iodine is an oxidizing agent. What that means is, even if this was an aldehyde at this point, it's going to now get oxidized by the iodine, and it will become, because of the oxidation, it'll become a carboxylic acid. So here's your iodoform precipitate, and then here is your organic byproduct. So we now heat under reflux, I'm just going to put heat, to form the propanoic acid. Now what I can do is I'm actually going to go directly to the propan-1-ol, and I'm going to do that through reduction. So I'm now going to do reduction with lithium tetrahydridoaluminate, LiAlH4, in dry ether. In dry ether under reflux. And the reflux is there is to make sure, because what's going to happen is that'll be converted first of all to the aldehyde and then reduced further to the primary alcohol. But we just want it to go straight there, so that brings me to the end of my synthesis. It's actually a very straightforward one in 2 steps, but that is a massive leap of faith. To use the iodoform to cut, it's grim. But that's how I would do it. It's going to be interesting to see that on the mark scheme. Let's go to the next one. Just devise a reaction scheme to prepare 2-methyl-butene from butanone using no more than 4 steps. Identify the reagents and essential conditions for each step and give the name and structure for the intermediate compound formed. Okay, now once again, this is a nightmare. We're growing the chain. What's up? Hi Ben, good to see you. Because there are Na plus ions. Oh, would we get the actual propanoate? Oh, yes, Winkit, you would. You're absolutely right. You would. So you could argue, Winkit. You could argue that, in fact, what we're going to get. So maybe I've not lost a mark there. Yeah, maybe we need to do this first. Oh, Winkit might have just saved me. I'm tempted to leave mine. It'll be interesting to see what they do with mine compared to his. He's correct. Now we're going to add a strong acid in the form of HCl to reprotonate that to form the carboxylic acid. Winkit, I think you might be right. I think I'm about to lose some marks on that. And then we can use LiAlH4 in dry ether under reflux. Dry ether. This one's just the addition of it. There's no conditions needed. It happens at room temperature. STP, standard temperature and pressure. Dry ether under reflux. Reflux. It's going to be interesting, that Winkit. Next one. So once again, we're extending the chain. The benzene booklet is killing me. So many pages. Winkit. Benzene. We know it's going to be there. We know it is. Make sure you check. Keep working on it. I don't think the booklet covers the reactions well enough. Make sure you've had a look at Chem Guide on reactions. I would definitely imagine they're going to appear. Right, from butanone. So I need, once again, they're starting with butanone. They're testing to see if I know how to grow chains. That's what they're doing. Oh, one was a cut, one was a grow. Now, you can't use cyanide in this case because you're going to form an amine. And the best you can get back to is a primary alcohol. It's a nightmare. Couldn't do it. So what we're going to do is we need to get to this guy. That's what we need to get to. This is what we need to get to. So we need to add a carbon. Yeah, so we're adding a carbon group, a methyl group. There's only one way, guys, to add a methyl group, and that's Grignard's. Yeah, so we're going to have to use Grignard's reagent for that. And the Grignard's, what Grignard's will do is it will add, I'll explain this in the diagrams. So the first thing we're going to do is we're going to make my necessary Grignard's. So this is one of the things I don't teach well enough in class. I'm still not perfect, still learning. which is Grignards is a bit complicated just because you can make any Grignards you like with whatever alkyl chain that you want to add. Now, I am going to add a methyl branch to that carbon. So what I need to now do is create the Grignards that will do that. So I'm going to need to have bromomethane. So I've chosen bromomethane because it contains the CH3 group that I want to add here. If this was a CH2 group, if this was a CH2, I would have used bromoethane. Yeah, does that make sense? So I've got to actually tell them what Grignards I'm going to make. So this is where we're starting with. I'm going to take the Grignards, methyl, and we're going to add it to magnesium metal. Now that reaction will effervesce, it'll do all kinds of cool stuff, but what that will make for me is CH3MgBr. Right, now that we've got that, we're going to add butanone. Add butanone and warm it. Oh, no. This needs to be in dry ether as well, because Grignards reacts with water. So we're going to do this in dry ether conditions. And what we're going to get is this. We're going to now have a methyl group attached here, and the ketone now becomes an alcohol. Now, the reason for that is because the oxygen in the original picture has a double bond, and it can no longer do that. Yeah, it can no longer do that. So it has to become, it picks up. I think actually what you actually have to do is you have to actually protonate it. So once again, you add it in dry ether and then you follow it by an acid. Yeah. But it's not really going to matter in this case, because now what we're going to do is we're now going to eliminate. Yeah, so we're going to dehydrate this. So what we want to do is, unfortunately, we're going to get a mixture of products here. We can't select for the one that we want, but I'm going to use concentrated hot ethanolic sodium hydroxide. And what that will do is we'll run elimination. Oh, hang on a minute, we can't use that. Can't do that, guys, because it's an alcohol. Oh no, can't do it. That only works with haloalkanes. Couldn't. What we're going to use is concentrated sulfuric acid. Concentrated H2SO4 under reflux. And it'll just remove water, dehydrate it, turn it into an alkene. So a horrible question, really grim, don't like it at all. 5 marks, no idea if I've got them all. We've got Grignards, 1 mark, condition, 3, 4, condition, maybe, might have my 5 there. We will see. Yeah, benzene, yeah, conc phosphoric. Yeah, you could use conc phosphoric if you like, Winkit. Totally fine to do so. Either one of those will work as a dehydrating agent. Absolutely. Right. This paper is long. Miles away from finishing as well. Not even close, folks. How am I getting on for time-wise? I'm up to an hour and a half. Too much teaching. Let's just get on with it. A yellow crystalline solid E dissolves in water to give a yellow solution. Addition of dilute sulfuric acid in the solution produces an orange solution F. So it's potassium dichromate. Yes, please. Which means it's potassium dichromate and potassium chromate. F is warmed. Warming F with ethanol produces a green solution and the formation of ethanol. Standard E cell for the right to left reaction, yada, 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 this to this. Deduce the formula of the ion responsible for colors F and G. Okay, so the orange solution is the Cr2O72 minus ion. This is F. Yeah, and G is the hexaquachromium 3. I love it. 3+. Nice. And then using this kind of give the E-cell value for the data book. Oh, okay. So now use your data book to give the E-cell value. Okay. To chromium 3. There it is. Number 28. Plus 1.3. I think 1.33 actually, wasn't it? Yep. Cool. Done. Next, write an overall equation for the reaction in the cell state. The state symbols are not required. Right. Okay. That's gross. Ugh. All right. So we've got Cr2O72 minus going to Cr3 plus. Is this acid or alkali? In dilute sulfuric acid. So this now there's H plus in the other equation already. So this one, to balance the equation, plus 7 H2Os plus 14 H pluses plus, I don't know, 6 electrons. Yeah, 6 E minus. Right, the other one is, and the electrons are on either side, that's nice. CH3, CHO plus 2 H pluses goes to, oh, and 2 electrons. Oh, it's on the wrong side. I need to flip it over. Flip it, flip it, flip it. Flip it over. See, oh, what the hell are they doing ethanol for that like that for? Bloody Edexcel. Hate that. CH3, CHO plus 2 H pluses plus 2 electrons. Right, multiply that by 3. 3, 3, 6, and 6. So electrons now vanish. All of those disappear, and that goes down to 8. Final answer. So 8 H pluses plus Cr2O7 2 minus plus 3 stupid ethanol formulas, which is not correct, by the way. I hate that. 2 Cr3 pluses plus 7 H2Os plus 3 CH3 CHOs. Whew, I'm done. Write the ionic equation for the reaction of the aqueous solution E with dilute sulfuric acid. Right, so Rosie Posey. Ah, Rosie, you're very welcome. Very, very welcome. I'm sorry that this webinar is going on so long, but it's a paper 5. They always take a while. So this one, guys, is your dichromate and chromate equilibrium. So you have orange Cr, and they actually want it in the direction that they like, yellow Cr042 minus, going in acidic conditions to form orange Cr2O72 minus. Switch that to black. So this is the, now I've got to weigh it. 2 chromiums, 2 chromiums. Water on that side for oxygen, and then 2 H pluses. And this makes sense, because if you add loads and loads and loads of H plus, you'll push the equilibrium back and it'll turn orange. There we go. Not redox, by the way. No change in oxidation states. Oh, wink it. Okay, guys. I now need to admit something to you here, guys. I had a flick through the paper, and I mean, like, I genuinely, like, I flicked through it. I'm like, flick, 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 flick. Before going through it on the way, I just checked that I've got the whole paper and that nothing's going to blindside me. And I know that seems like a bit of a cheat, and some of you might think that I'm cheating. I never look at the mark scheme. I just flick through going, yep, 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 because I like to make the mistakes. Making the mistakes is where the value is, because I get to fix the mistakes I made. But I found this question, and that took a while. Yes, it did. Right, wink it. I'm going to attempt to explain this, and if I get it wrong, it's over to you. Okay, So it's given us a whole load of information. It says, using an excess of oxygen, which is what causes me all the problem, 25 centimeters cubed of a hydrocarbon of CXHY was burnt completely. So what we've just done is we've just taken a hydrocarbon, we've just taken CXHY, and we have burnt it in excess O2, which is going to be a problem because it means that trying to run moles on it will be tricky. Excess O2, and it's going to become CO2 and water, CO2 and H2O. Right, now the problem is we've also got excess oxygen in here, which is the problem. But what we're now going to do is, what they now do is step number one, by the way, they had 25 centimeters cubed of that fuel. What they then did was they cooled this. After cooling the room, cooling it down to room temperature, it was found that it decreased, the total volume was measured and found to be 75 centimeters cubed less than the total gas before ignition. And there's my first bit of info. So out of this balloon, this is a gas, but if I cool this, water becomes a liquid, and the balloon will shrink in size. So we have now been told the amount of water. So I now have, and there's this big horrible equation. I can now say that I have got 75 centimeters cubed of water. Next, when the products of the gases were shaken with potassium hydroxide, the total gas volume decreased by a further 100. Now, potassium hydroxide is a base, and that will react with carbon dioxide, and that will turn into potassium carbonate, and it will remove it. So we've just been told the volume of oxygen, CO2, that's 100. So we've all of a sudden got some numbers for people in here that we can insert. Yeah. The next thing is we've also got 25 centimeters cubed of the fuel. And we need to work out the value of X and Y. So that's, can I just point out, this was already difficult because you had to recognize that the decrease in temperature is going to cause water to become a liquid. And you need to know that the potassium hydroxide was going to remove the carbon dioxide. This is already challenging. If you didn't know that, you're already done with. If I were you, just to completely make this completely transparent, in an exam, I would have bailed on that question. I'm just looking at this going, nah, this is way too complicated for 3 marks. 3 marks! 3 marks, 3 minutes? No, not even worth the time. But anyway, so now that I've got that, the first thing that I can point out to you guys is in this equation that because I often teach when students get gas questions with multiple choice, they often talk about this idea of changing volumes of gases. And the first thing that we can say is that any 1 mole of gas occupies 24 liters cubed, 1 mole of any gas. What that means is that moles and volume sizes are directly proportional. So if I was given 25 centimeters cubed of my fuel, I can treat that like it's moles. Yeah, I can treat it like moles. Now, what you'll realize is that X in this equation is the same as the X in the CO2. And what you'll notice is that 1 mole of my fuel, I'm just going to call, let's just say that 25 centimeters cubed, just for giggles, is 1 mole. Yeah, we're just going to call this the mole. In fact, let's just say it's 25 moles. Yeah, let's just call that 25 moles because it means that we can just get rid of the centimeters cubed out the window. Yeah, moles. Just get rid of the centimeters and replace it with the word moles. Okay, so now the great thing is that 100 moles there is caused by the 25 moles of carbon causing 4 times, because 100 divided by 25 gives me 4. What that tells me is that X equals 4. The reason being is because my 25 moles at the beginning, yeah, which has a 1 in front of it, yeah, my 25 moles has been multiplied by 4 to get to the 100 moles, which means there's a 4 in front of there. Yeah? Now, to get to the water is a bit more tricky. Yeah? Because what we realize is it's a ratio of y/2 to get to 75. Now, this is where I start to get a little bit muddled here. So what we now need to do is we now need to solve for y. So what we can now do is we can take this big disgusting equation and start inserting people I can deal with. So the first thing is I'm going to get rid of this guy, which means I'm going to do it as 25. So green, 25 plus. Right, now we've got x plus y/4 O2. Well, what we also know is that the x is inside the bracket. What that means is if I were to do that, I've got to treat this as if x was outside the bracket. By the way, that is a horrible concept, and I'm really sorry for that, because people are going to ask me, why is that? The reason being is this is a multiplying factor of the original 25 centimeters, because the ratio is 25 to 25 multiplied by that disgusting thing. Yeah? Which is the really grim bit. So this becomes 25. I'll do this. I'll try and color code this as best I can because it's really grim. Yeah. So the next bit, which is I'm going to do in, I don't know, orange, this bit now becomes 25 multiplied by brackets x, so I don't need to multiply, 25 x plus y/4. And the O2 that disappears because I don't need it there, because it's basically that the whole thing is O2. Yeah, that's O2, and this is the fuel. That's the CXHY. Right, now all of that now goes to, now the great thing is we've solved for the 4, so we know the mole ratio, so I can now just insert 100 because I'm using the centimeters cubed as if they're moles. So I'm now going to plus this to the 75 moles of water, but we haven't solved. Now that's the problem. That Winkit we discussed for a while to realize that this is a nightmare, because you want to multiply that by it, but in fact you're not. You're multiplying y by 2 by a value to give you 75. So this multiplied by x gives you 75, so I can just insert 75 straight in. What a nightmare. Yeah, the whole thing is a trap. Right, next thing, sum up all your values. So this now becomes 175 minus the 25 from both sides to make that one vanish, which means I can simplify this whole thing. Winkit probably telling me I'm doing okay, or maybe not. He's probably saying, sir, you stuffed this up. It's probably what he's actually saying. Oh, it's completely different. I can sum all this up now to become 25. I'm sorry, I've stopped color coding it. I do apologize, guys. 25 brackets x plus y/4 equals, so that became 150 minus it equals, so that becomes 100, equals 150. Right. Now divide everybody by 25. Divide everybody by 25 and the 25 vanishes. Yeah, I should be doing this stage by stage, but I'm not. So the 25 now disappears. Yeah, divide everything by 25. If you're not watching this, I'm not showing my steps very well, am I? Divide 150 and divide 150 by 25, and I get 6. So that now becomes 6, and the brackets now vanishes. Now I can do, oh, I don't know where my x is. The x was, where's my x gone? Oh, my x is 4. We know that it's 4. So I can sub in my x with 4. Right, bring that over to there, which becomes minus 4. So now I then have that equals 2. Yeah, and now multiply both sides by 4 to make the 4 vanish. So y equals 8. Guys, I'm not going to lie, for 3 marks, Edexcel, it's just disgusting. Wasting my time. When CX was added to a little bromine water and the mixture shaken, the bromine water remained yellow. Okay. Back to chemical tests, back to something real. C4H8. This is disgusting, because if you got it wrong, you were royally screwed. Wow. I know, right? That's an alkene, but it's not an alkene because it didn't react with bromine water. It's cyclobutane. Or, and they want 2 possible structures. It's the most disgusting question I've ever seen. It's not even chemistry, by the way, guys. It's maths. It could also be methyl cyclopropane. Can I just point out, I would write to Edexcel about that question and say how unfair it was. Because I skipped that because I ran out of time. Yep, darn it, I would have skipped it in an exam too. I would have got it wrong in the exam. Compare and contrast the mechanism of action of platinum as a catalyst for removing pollutants from the, and vanadium 5 oxide. Okay, so first things first. Right, so the platinum one is carbon monoxide plus nitrogen monoxide, and this has a platinum and rhodium catalyst, by the way, which is a heterocat, and we're going to form CO2 and nitrogen gas, and then balance, I believe. The other one, V2O5 is a solid, and that reacts with SO2 gas to form SO3 gas, and then and V2O4 solid. This is also a hetero. V2O4 solid reacts with oxygen gas to form V2 to regenerate my catalyst. They're not the same process. It's a very interesting question. They are both heterogeneous catalysts because they're in different phases. Both heterogeneous catalysts. However, differences. Platinum in catalytic converter has active sites. Have active sites that bind reactants, weakening bonds, and then releasing products. Not releasing, desorbing products. Whereas, unlike V2O5, which reacts directly. I have no idea if this is what they want. Are we allowed to write in points like that in an exam? Yes, you are. You are absolutely fine to give bullet points. Yes, completely. As long as you give quality sentences, your boy. Yeah? You've got to make sure you can't just write one word. It needs to be solid sentences, but of course you can use bullet points. Absolutely. Yeah? Unlike V2O5, which reacts directly with, I think I'll get the marks from the equation, with SO2 to produce SO3 and V2O4, and then V2O4 reacts with oxygen to reform catalyst. Lots of catalysts on this paper. Wow, that was long. Section B. On to section C, organics. Right. Where's my question? The bonding, okay. Another way of drawing structure in caffeine is shown below. So, okay, so that's that one, and that's this one. So they've replaced that with a ring. So they're saying it's delocalized, like benzene. It's a play on benzene, this, folks. Yeah. So it says, so explain what differences, what this diagram indicates about the bonding in caffeine, stating the effect on the structure of caffeine. Okay, so the ring, bullet point number one. Bullet point number one, Danny, you're going to bullet point this nice and clear. Yeah, you're not going to do one words. Yeah, but you're just going to complete sentences with bullet points. Yeah. There is, capital T, I may as well do it properly. There is a delocalized electron system. It's a pi system, by the way. Yeah, full stop. There is a delocalized system. Yeah, right. So what that now means is that there's a pi bond, pi bond, pi bond, pi bond, and pi bond, and they are all overlapping with each other. Yeah, like the sandwich does in benzene. Yeah. So what that now does, just like in benzene, yeah, you're going to have bond lengths are going to vary, because what's going to happen is instead of having in benzene, you always talk about with benzene's structure and bonding, you talk about the double bonds being short and the single bonds being long. Benzene should be the Superman symbol, but it's not. This is because it's a delocalized system. In benzene, the bonds are all exactly the same length. And that's what they're wanting you to do here. That the carbon-nitrogen bonds are all going to be, we could even just say that they're all going to be approximately the same length. All bonds in structure are now the same length, the same length, but an intermediate, but of an intermediate length, but of an intermediate length. So what actually happens is that the length of this bond in benzene, the length of this bond in benzene is longer than the short double, but is shorter than the long single. It's an intermediate bond length. You've got a short double, an intermediate benzene, yeah, which is like you can imagine it being like this if you like, is the circle, and then the long single bond. Yeah, it's an intermediate bond length. Next thing is it's going to be planar around those atoms. Yeah, it will be planar in its arrangement. It will be planar. It will also have increased stability. It will be planar. It will have increased stability. The structure will be more stable. Stability. It'll also go through different iron. What unit is this? Unit 5 for A2. Increased stability. I'm going to stick with that. We're done. Next, suggest why caffeine is a much weaker base than a primary amine such as ethylamines, even though the right-hand ring has 2 amine groups. Caffeine is a much weaker base than a primary amine. Oh, we would have done this today. We've already discussed this. So, primary amines. Just to explain why. So we're saying that the amine group, which is here, by the way, that's the only one that can act as a base because, oh no, that one could also act as a base. And so could that one. I tell a lie. That one can't because it's got 4 bonds. But This one can't act as a base very well because the lone pair is what's joining the ring. Oh, that one can't either. Lol. Huh. Oh, maybe. That's weird, isn't it? Should be in an H2 group, but it's to be an H1. Oh yeah, neither of them can act as a base because there's an invisible H on the end of this, isn't there? And that's been sucked into the ring. This one had no hydrogen, but they've been sucked into the ring. Yeah, this one can act as a base, and that one can act as a base still. Anyway, so they can't do it. Unlike a primary amine, yeah, it's a much weaker base than a primary amine. The lone pair of electrons the lone pair of electrons on the nitrogen is incorporated into the delocalized ring system. So electrons less available to act as a proton donor, proton acceptor even. Done. Next, okay, a 200 centimeter cup of coffee contains approximately 25 milligrams of caffeine. Okay, calculate the concentration in moles per dm cubed of caffeine in a cup of coffee. Do you know what? Funnily enough, will you do the June 2021 papers? I don't have them, Ian. Speaking of coffee, has anyone else realized yet that I've been going for 2 hours and 1 minute? Okay, I've got a 200 centimeter cube cup, 85 milligrams. I want moles per dm cubed. Okay, so first thing, let's deal with the moles. 85 milligrams. Well, I've got to get to grams over rams, don't I? I've got to get to moles. But the first thing I'm going to do is I'm going to convert this to grams. Divide by 1,000. So I'm going to get 85, divide that by 1,000. I'll never do anything in my head. It's not worth it. Not worth it. 0.085 grams. Right, how much does caffeine weigh? Has it given me the MR? Be nice of them if they had. If they haven't, I'll just be rather irritated. They actually haven't. Right, M8. Those haven't been released yet. Nope. Yeah. Anyway, turn this into a molecular formula. They have, LOL. Carbon, carbon, carbon. Right, so I've got C, 1, 2, 3, 4, 5, 6, 7, easy to miss one. I've got C7, H, well, let's do the H's. None there, 1 here. Nope, none there, 1 here. None there, nitrogen makes 3 bonds, none there, none there. 1, 2, 3, 1, 2, 3. This is grim. Oh yeah, 1, 2, 3. I've missed the carbons. I missed a carbon. Look, missed him. So I've now got 1, 2, 3, 4, 5, 6, 7, 8. So easy to do. It's why you have to draw them on like this. So then the hydrogens are going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is grim. And then oxygens are 2, and then nitrogens are 4. Grim. Hate that. Grab you. Oh, darn it. Grab you. Come on. Come on. There we go. Not enjoying this, is it? My laptop's really struggling. It's getting hot, that's why. It's grim, that. It's really mean the fact they haven't. Got to go back all those papers. Right. Now, I think I may have a correct formula. Let's work out the MR. 12 times 4 plus 10 plus 16 plus 16 plus 4 plus 14 times 4. Oh, what? 12 times 8 plus 10 plus 16 plus brackets 14 times 4. 178. 178.0. Right, grams over rams over 178.0. 0.085 divided by 178.0 gives me 4.775 times 10 to the minus 4 moles of caffeine. Right, now I'm in, I've got that in 200 centimeter cubed cup. 200 centimeters cubed. Well, if you want it in a liter, yeah, to go from there to 1 dm cubed, yeah, I need to multiply it by 5. So I'm just going to multiply my answer by 5. And I'm going to get an answer of 2.39 pound, 39 times 10 to the minus 3 moles per liter. So I'm going to get, the marks are going to be 1 mark for him, 1 mark for the conversion to grams, 1 mark for the moles, and the other mark for the times by 5. Okay, seems reasonable. The removal of caffeine from the body is first order reaction with a half-life between 3 and 7 hours. The adult coffee contains 160 milligrams of coffee. Good. Do you want the June 2021 papers? Huh. Yes, I'd love them, Aryan. That'd be very useful. Yeah, send them to me. I'm not going to go through them. I'd get shot by my school if I went through them. Wowza. Yeah. Anyway, moving on. The removal of caffeine from the body is first order. 160, calculate the minimum time needed to remove it down to 20. Okay, the minimum. So we've got to go between 3 and 7. So we take the minimum. So we've got 160 milligrams after the cup of coffee. After the first half-life, after 3 hours, yeah, it will have dropped to 80 milligrams. Yeah. After a second half-life, it's first order, 3 hours. That's kind of the point. First order reactions, the half-lives are consistent. Yeah. So 40 milligrams, and then another 3 hours gets me down to 20 milligrams. So the total number of hours is 9 hours. I'm done. Moving on. Next. Chlorogenic acid is an ester of caffeic acid. A compound that is present in all plants. A student suggests that caffeic acid could be synthesized by electrophilic substitution of 1,2-dihydroxybenzene. Draw the mechanism for the formation with the suitable electrophile. Okay, can. So first thing, let's draw us 1,2-dihydroxybenzene. I'll put the other hydroxy up here. There we go. I don't really like doing that. I hate not showing sticks in mechanisms. So you're just asking yourself for trouble if you don't do it. 1,2-dihydroxybenzene. I now need, so you can see the 1,2-dihydroxybenzene there, and this is what I need to add to it. So let's now convert that into an image. So that's now going to become C carboxylic acid, just going from this way backwards. Yeah, going to that C, double bond that C, and then it joins on. So that one's going to have a H on it. This one's going to have a H on it. And then it's also got to have had a Cl. That's why. Okay, so here's what's happening, folks. The first piece of skill I'm doing there is just converting this image into the two people I need, and then realizing that I need to join it. I need to join it at this point here. That's where I need to put it. So what I now need to do is I need to write an equation for the electrophile, and what I need to do is I need to remove this chlorine. So I'm going to have I'm going to actually reverse the equation. CHCl, that's this guy here. Yeah, CHCl, I'm going in this direction. Cl goes to CH, damn it, didn't want to do that. Goes to CH and COOH. Now what I'm going to do is I'm going to add AlCl3, because the AlCl3 is going to remove that chlorine. And I'm going to form CH, the plus is now on that C, and I've now got CHCOOH. Now I can do the mechanism, and I need to put it on that location. So what I'm going to do is I'm going to draw out my benzene ring, and I'm going to go circle, and I'm going to want to put it here. So I'm going to draw an arrow from that, leaping over it, going to that now positive carbon, which has got a H, and a CH, it's got a double bond as well, going to COOH. Didn't really want to do it like that, but whatever. I'll have to clean that up a bit. So H there, and then a COOH. So that now reaches over to that, and I now need to put my OH here and my OH here. Right. Mechanism continues. I now form this structure. The ring is broken. Yes, I've now broken that ring. It's a terrible benzene ring, a bit flat on that bit there. There we go. So that's now positive. I've now got an invisible H has now appeared. And I now have this crazy structure attached to it. This crazy structure. All of the rest. Right, and now that folds back in, and I'm done. That's it. It's a really gross thing, guys. Really, really grim. Yeah, not very nice. Do I need to regenerate the catalyst? Oh. Right. Next, I've given you these horrible diagrams. What have they added? So this bit is this bit. It was an OIC. It's now an ester. Okay, so just convert it into an alcohol. Yeah, so it was an alcohol at that group. So we've got, okay, just, yeah, quinic acid. Caffeine reacts with quinic acid to form caffeic acid to form chlorogenic acid. So draw a hexagon. It's not benzene, by the way. It's an OH here, OH here. That must have been an OH there. Yeah, and then an OH up here, and then a, oh, it's really weird. There we go. Next, NMR. I'm coming to the end now, folks. I'm on the last question. Right at the end. It's been a long paper, this, guys. 2 hours and 12 minutes. I've still got to mark it, too. Structure of acetylene. Oh. Identify the other proton environments of acetylene on the structure and label them B, C, etc. So, shown one proton environment. So those, just to explain what it's doing here, it's quite a clever question, really, because it's skeletal, and they're saying the fact that you've got H's attached to this guy here. Well, there is no H's there. It's a ketone group, so there's no hydrogens. There is a proton here. There is protons on there, and there is, of course, at the end. So your first identified one, your second identified one, yeah, your third, you know what, they'll be very interesting to see, because that one there, and then this one here, they're not showing the H's and that one there. So A, B, C, and D, okay? So the splitting of A is there's nothing next door, yeah? It's nothing next door. So the splitting is a singlet, nice and easy. Next, the splitting of B is also a singlet because it's on an OH. You can't be split unless you're on a carbon. C, now that can be split, and that's going to be, C is going to get split by D. This is going, because this is one hydrogen here, and there are 3 hydrogens on here. I wonder if they'd care if I did that. Yeah, I don't mind if they've done it. Or that I'm doing it. So this one's going to be an integration of 1, but split into a quartet. So C, integration 1, but split into a quartet. We know that NMR is going to be on your paper. D is going to be an integration 3, but a splitting pattern of a doublet. Singlet, doublet, triplet, quartet, quintet, sextet, heptet. That brings us to the end of the paper. Finally, I wonder how long the paper is actually meant to be. Is it meant to be an hour and 45? I have been doing a lot of teaching during this process. I hope everyone realized that. I'm sorry if you got bored and have disappeared. I don't really care, if I'm honest. All good, Mr. Duncan. Good chat. Yeah. Right. Let's now find the mark scheme. I do have the mark scheme for this paper somewhere. Documents. IAL papers. A2. I knew this was going to be a long one. It's probably the most important one for my students, though. Right, let's go through the mark scheme, see how many of these I get wrong. Green. First question, B. Second question, A. Third question, C. And then C followed by 3B, which is a B. I like it. Next, this one I didn't like. 4 is D. Yes. Okay, fuels are at the anode, and the fuels are always being oxidized. Better to learn now. Next, chromium A. Stable ion with a partially filled D, 6C. Tetrahedral and square planar, D. B, they're dative. A, anhydrous is blue and water's pink. Question 9 is D. Question 10 is D. Question 11 is B. Question 12 is C. Question 13 is C. Question 14 is A. Question 15 is D. Question 16 is B. Question 17 is C. Question 18 is C. I finally got one wrong. What did I do? Oh, I didn't see the yields. Oh, I didn't see the yields. They knew I wouldn't see the yields. There's yields in here, folks. Oh, so you had to step it all the way through. So I'll fix this now, guys. Easy. See, I'm as fallible as the next person. So they have given me 8.24 grams of him. Yeah, and that was a 60% yield from this guy. Yeah, I missed the yield entirely. So the first thing I want to get to is I want to get to moles. So I want to get to moles. So I'm going to do grams over rams. 8.24 divided by 122 gets me to 0.0. I thought it was a bit too easy. 75. Now that's the moles, but this was a yield of only 60%. So what I want to now do is get to that one by dividing by 60 and timesing by 100. Yeah, step 1, step 2. So divide that by 60 gets me to 1%, times by 100 gets me to my actual number, which is 0.112. Oh, hang on a sec. Yeah. So that gets me to 100% yield. Oh, okay, that's quite clever. So that's just, this is the 60%, yeah, of that second reaction. So 100% would have been 0.112113, and that now then I would have had 0.113 of that much, but then that was only 40% yield. That was only a 40% yield. So what I need to do is get that back to 100 as well. So divide that by 40 gets me to 1, times it by 100, and I should have had 0.281 moles, which I can roll over to here. And then I've got that many moles of it, times by 78, and I get an answer of 21.95, which is none of the answers, but I'd pick C because it's the closest. Lol, I've done a calculator mistake there somewhere along the lines, but it's okay. Fine. Section B. Oh, this is going to be grim. Okay. Zoom in. So oxidation state 0. It doesn't give any of the oxidation states. Well done, you idiots. Yeah, 0 copper, hexaaqua copper 2, copper 2 hydroxide with my tetraaqua, and then copper 2 oxide, and then the tetraamine diaqua, and then the same thing. Oh, I've made a mistake. Oh, yeah, that's a +1 because it was invisible. Yeah, ignore water ligands. Yeah, it's absolutely fine. State 1 because it was colorless, and then number 2 was back to my copper 2 hexaaqua. These are all types of complexes. This one was gross. Color, transition promoted electrons between subshell stroke orbitals. Copper 2 orbitals are partially filled, so electron transitions are possible. Copper 1s are full, so no electrons can move. Yeah, V2 has a V contains copper 1 plus, full D subshell. Orbitals are full. So electrons cannot become excited, switch back to being green. Yeah. Cu2 plus has incomplete D subshells. So electron so become excited and absorb it. Yeah, I've covered it. Covered it in the previous sentence. Cu1 plus is oxidized by oxygen in the air. Oxygen reacts with Cu1 plus. Balanced ionic equation. Give an example. There you go. Next. With their values next to it. And then the overall charge with the final value. I like it. Still some questions here which are going to be grim. Final answer, n equals 2. I like it. They'd give me all my marks if I get the right value, especially with all my working shown. You must show your working, by the way. Yes and yes. Thank you very much. Any reasonable species, an ethyl, a methyl, with their charges. Right, transformation, reaction of butanone with iodine and sodium hydroxide forms sodium propanoate. Well done. Did they allow? No, they didn't. I would have lost one. Thanks, Winkit. Yeah, add dilute sulfuric acid. That brings me back to propanoic acid. Yes, well done. And then accept any identified strong acid. Ooh. Next, lithium tetrahydride will eliminate. Dry ether. Fine. Thanks, Winkit. I definitely would have lost one there. Identification of suitable haloalkane. Reaction with magnesium powder and dry ether. Oh, blimey. And then, so that's not correct. The dry ether should have been up here. Yeah, and then to form grignards, formation of 2-methylbutanol, reaction with concentrated sulfuric acid to give the alkene. Under reflux, probably do. Grim. E cell, final voltage 1.33. Left one minus right one. Oh, equation relating each to half cells and determination. Oh, okay, so I needed to actually show them the calculation for that. Damn. Show calc next time. Show calc. Easily said. That just didn't. Identification of F and G is 1 mark. Oh, no, I still get those. So I will show the calc next time, though, using Earl. Correct equations and species. Oh, yeah. 3 and 2 and 1 and all that jazz. Dichromate. Chromate to dichromate. Y equals 8. That disgusting thing. It's really grim. Ugh. Horrible. I wouldn't have got that in an exam. I am not pretending like I would have. Guys, I'll take those marks off myself, but those two I definitely would get. And then this one was gross as well. A load of waffling on this one as well. Both platinum are both heterogeneous. There is absorption of reactants on the catalyst surface. In the catalytic converter, absorbed reactants are weakened, bonds broken, reactions occurred. Step 2, desorptions. They wanted a full explanation. Has active sites that bind reactants. I needed to say adsorb reactants, weakening them, and then desorbing products. I almost would have gotten there with weakened bonds and then desorbing with reaction. I needed to give more detail on this, guys. More detail on this one. Yeah, adsorb, weaken, react, desorb. Yeah, and then reduced SO2 reacts with oxygen. My equations get me the second one. Nearly at the end now. It's going to be interesting to see if I've counted everything right. There is a delocalized ring system. All bonds undergo, all CN bonds allow, all bonds will be the same length. Thank God for that. Yeah, planar, not there. Increased stability. Caffeine has stabilized energies. Don't like that. It's garbage. They've talked about reactions in the mark scheme, but then they've not asked us to talk about reactions there, which is really mean. Increased stability. Stabilized energy. The lone pair of electrons. Lone pair. Oh, the lone pair. Effective delocalization. They should incorporate into the locality, making the reference to them less available, will always be increases available alcohol groups. No marks scored if input. Availability of the non-conforming. Huh. It's weird. And reduces lone pair availability. Did I get the right answer? Oh, I've made a mistake. The MR was 194. I miscounted. I didn't. I just miscalculated it. I had trouble with that. They've calculated it as 194, and I calculated 178. 12 times 8 plus 10 plus 16 plus 16 plus 14 times 4, 194. Yeah, okay, there's my error. There's my error. So error carried forward. So I would have scored 3 then of the 2. 3 of the 4. That sucks. Hate that kind of question. Calculate the number. 9 hours. Fine. That wasn't very complicated, was it? Horrible mechanism. ALCL3, reaching out. Yep, fine. Intermediate. Yeah, equation. Curly arrows. All good. Stupid quinoic acid. Quartet, doublet, singlet. And That's the end of the paper. Right, guys, I am done. I am so very, very done for today. It has been a very, very long webinar, 2.5 hours. Right, guys, I hope you found it useful. Yeah, hope you find it useful. Good luck with your test coming up. I will do paper 6 at some point this weekend. But otherwise, guys, have an amazing rest of your day. See you later, Winkett.